Good afternoon, everyone. Welcome to today's webinar, jointly organized by PolyU and Hong Kong IE Civil Division. Today, we are very honored to have Professor Elghazouli to share with us on the topic seismic design concepts for building structures. Professor Elghazouli is a global STEM scholar and chair professor of earthquake engineering and structural integrity. Before he joins PolyU, he was the head of structural engineering at Imperial College London. He also worked for several years in industry at Edinburgh University. Professor is an expert on seismic design and structural robustness. He has produced over 400 publications in related areas and has been involved in the design of notable structures worldwide. He is a fellow of the UK Royal Academy of Engineering, a chartered engineer, and a fellow of the UK Institutions of Civil and Structural Engineers. He leads and contributes to several international co-development committees on seismic design. He was a former chair of the UK Society for Earthquake and Civil Engineering Dynamics and UK delegate to the International and European Association for Earthquake Engineering. Without further ado, may I now invite Professor to present. Professor, please.
Thank you very much, Henry. So I'll just start with a few slides presenting the Department of Civil Environmental Engineering at PolyU. So just a few slides showing the standing of the department in terms of being ranked one of the highest in the world, and also, of course, one of the highest in Hong Kong, according to different ranking systems. We have top scholars ranked depending on how the work is used internationally, and these are a list of some of the professors at PolyU who are included in this ranking. We have several members of the department who are members of different academies, and we have different measures of esteem in terms of very large prestigious grants won by several colleagues. And we offer a number of programs at undergraduate level. We offer programs in civil engineering as well as in environmental engineering and sustainable development. And similarly, at MSc level, we have programs in civil engineering and in environmental engineering. And of course, a lot of research students are studying for their MPhil or PhD. We have a lot of outstanding alumni. Some of them are shown in the screen here, working in industry and in the public sector, but there are many others. And of course, you can find a lot of information online if you wish to know more about the department. Now, I'm going to start my presentation, which is really given this very general title of seismic design concept for building structures. Now, I know that there are several hundred people attending this webinar, and I guess that there are quite a mixed background. So what I'm going to do here is just really give you an overview of seismic design and assume you know very little about seismic design, but of course, I'm very happy to answer questions at the end, and hopefully there will be some time available for this. So in terms of seismic design, at the end of the day, overall, what we're trying to do is reduce the risk from earthquakes. And this risk can be represented as a convolution of hazard, vulnerability, and also consequences of the damage or losses that are incurred due to earthquakes. Now, hazard, of course, is something that we try to predict as much as possible. Vulnerability is what we try to reduce as structural and geotechnical engineers in order to reduce the risk. And of course, we have to understand what are the consequences of damage or losses happening in a structure in order to design it in an appropriate manner. Field observations or experience are very important part of our work, because with whatever we do in the laboratory or in simulations, it's not going to be the same as understanding from what happens to structures in a real earthquake. So Our work involves, of course, expertise coming from the engineering seismology and geology side and structural and geotechnical engineering side. I'm very much a structural engineer, but I'll try to give you in a few minutes some very basic general understanding of what seismic hazard would involve. So I'll start by the hazard side in order to see how we really work out the loads that we design for in codes of practice. So if you look at global seismicity level, this is just a map of the world showing notable earthquakes that have happened over many years since 1900. And you will see that earthquakes or large earthquakes are clustered around what we call plate boundaries. So the earth crust is consisting of relatively rigid plate, and then these are typically moving relative to each other. And earthquakes happen at, or large earthquakes happen at these boundaries, but it doesn't really mean that earthquakes or notable earthquakes don't also occur within the plates themselves. But typically the very large ones occur at the boundaries. So why do we get the earthquakes? Because obviously, if you look at a cross-section of the Earth, you will see that they are consisting of different layers. And these layers here in this top figure have different density, they have different temperatures, and there are always continuously materials going from the inside of the core to the outside. And then as they get cooler, as they go to the outside, they are trying to go inside. There are always currents that are occurring, and this creates tension or compression or movement at the surface. And that is the problem where this movement is held. You tend to build a lot of energy. And once you get this fracture over faults, you start generating quite a lot of energy. And this is expressed in terms of vibrations that translate over large distances. So this figure here on the left shows a typical fault situation. Of course, this is the source here. And typically what we see on the surface is the fault scarp. Sometimes we don't really see the fault on the surface and it is buried inside. But what happens if you look at a typical fault situation? In the top figure here, you start building this energy or elastic energy within the fault. And then when it reaches its capacity, it snaps and you release very large amounts of energy within seconds. So it's built over decades, but then it is released in a few seconds. And that is what creates an earthquake, or the main mechanism of earthquakes. Now, of course, in many cases, you see it at the surface like this. Sometimes you have a vertical shift of a few meters, but the fault itself might be extending over tens or hundreds of kilometers. And of course, the larger this break within the fault, the larger the amount of energy, and the amount of energy is related to the magnitude or the typical magnitude that we characterize the earthquake with. But it's important to realize that the magnitude is related to the event itself and not where you measure the vibrations. Of course, the vibrations will reduce as you go away from the source. So what seismologists will typically do, they will study these mechanisms of earthquakes. They would look at the nature and location of these earthquake sources. They will look at the frequency and magnitude of these events from that particular fault source, and they will look at what is the likelihood of a certain magnitude occurring within a certain number of years. And this is what we would refer to as magnitude frequency relationship for the source. And of course, as you go away from the source, if you're interested in a particular site, then you will get attenuation with distance. So the vibrations would tend to reduce as you go away from the source of the earthquake. But of course, they do attenuate, but it depends on what is the travel path. It depends on what kind of soil conditions are existing, what is the topography of the site that you have, and so on. There are a number of factors that will influence this level of attenuation, or in some cases, magnification. But at the end of the day, if you do this assessment for a particular site, you can determine what is the expected ground motion at that particular site. Now, of course, in many cases, your site will be influenced by more than one source, and hence you will have to do a probabilistic seismic hazard analysis where you look at the possible influence of several sources and then predict the hazard based on the influence of these different sources. And that's what we would typically refer to as probabilistic seismic hazard analysis. Now, if you have a very important structure that you're designing, you would actually have to do this kind of exercise for the site. But for the vast majority of normal structures, the codes will try to simplify the situation, do the hazard for a particular region in advance, and then give you what we refer to as seismic hazard map or microzonation maps, which will give you the expected maximum accelerations for a particular region based on its location within this map. So things will be quite simplified for normal, typical type of structures. But I have to, of course, say that this is very, very uncertain. Seismic hazard assessment has a lot of uncertainty in it. And what I'm showing here is a slide, a very well-known benchmarking exercise, where they got 13 experts, try to work out what is the peak horizontal acceleration that you get at a particular site and the annual probability of exceedance of these accelerations. And you will see vast differences, maybe 2 or 3 or 4 times difference between these different experts. So we are dealing with something which is very highly uncertain. And hence, when we are doing our design concepts, we have to take into account this uncertainty in the loads that we are predicting due to earthquakes. And this is really very important to realize that seismologists would do their best in terms of predictions, but there is very, very large uncertainties. Now, I would just want to say a few words about Hong Kong. I haven't been in Hong Kong for a long time, but of course you hear a lot about the seismicity of Hong Kong, and there is lots of debate about the level of seismicity. It is clear that it is low to moderate. I would say that it is probably, in terms of risk, it is a moderate level of risk. It seems that the estimated peak ground acceleration for an earthquake that might happen every 500 years is around 0.12 G, which, according to typical seismic codes, that's moderate level of hazard. It's not low, but within the moderate level. And my understanding is that there is a national seismic code that is likely to be issued quite soon. But there are quite a lot of issues involved here. But what I can say is that the hazard is not insignificant. It needs to be taken into account, particularly for important structures. Now, it is important, having said all that, to emphasize the importance of soil conditions. So if you are in a site and you're looking at the underlying soil below the structure that you are considering, the soil conditions play a very important role. So what I'm showing here on the left and on the right are the measured accelerations, or if you like, the vibrations, in very close sites, just within a few meters from each other. But one is in rock soil and one is in soft soil or alluvium. And if you look at the accelerations, they are orders of magnitude different from the rock and the alluvium, and that's because of the magnification effect that you get from softer soil conditions. And although you get significant attenuation with distance from the source of the earthquake, the soil condition can amplify this quite significantly. And of course, that is very important, and it can make a massive difference to the behavior and the loads that are acting on the structure. Typical examples of this effect is what happened in Mexico City. There was a very large earthquake in 1985. And during this earthquake, a lot of buildings were damaged. And the important thing is in Mexico City that it is an area which is filled by soft soil in an old lake. And hence there is very soft underlying soil conditions, which of course magnifies the accelerations quite significantly. Interestingly, the 1985 earthquake was almost repeated more or less on the same day in September 2017, and very similar levels of damage also occurred. So it is a well-known effect, and it happens in many parts of the world. Probably another very close example in our memory is what happened in the collapse of a building in Bangkok in March this year, where again, in Bangkok is about maybe 1,200 kilometers or so from the earthquake that happened in Myanmar. So you would expect at 1,200 kilometers that you don't really get significant seismic accelerations from the earthquake. But because it's relatively soft soil conditions, there's been very significant magnifications of the accelerations within this building, but of course coupled with a lot of vulnerabilities in the structure. There are many issues in terms of design, materials, and detailing, and so on, that led to the collapse of the structure. So at the end of the day, we can measure, of course, now through networks, we can measure strong motion in terms of acceleration, velocity, and displacement at locations which are distributed depending on the location of these instruments. And we can determine exactly what are the accelerations in the 3 directions, in the 2 horizontal directions, and also on the vertical direction. Typically, the vertical component is not that important in terms of the design of structures, unless it's a very large earthquakes and you are relatively close to the source of the earthquake, and also depending on the type and configuration of the structure that you are looking at. But in any case, we have very good measurements now, and we have very large databases that gives us what kind of earthquake strong motion records are available within different parts of the world. Of course, the problem is we don't know the earthquake in advance, and we have to rely on a lot of predictions in order to work out what is likely to happen in a certain region. Now, while you can measure the accelerations and in terms of the history of the acceleration, it is very convenient for simplified design to work out the forces based on what we refer to as elastic response spectrum. So if you know the acceleration record, then if you run a single degree of freedom with different periods of vibration, and you look at the response of this single degree of freedom system, and you plot the response acceleration against this period of vibration, you will get this elastic response spectrum. And of course, that response spectrum will be for a particular level of damping within the structure, and it is assuming a single degree of freedom. Of course, real structures are rarely just a single degree of freedom, but it gives us a very good idea about the frequency content of that particular earthquake record. But of course, again, this is if you know the record in advance. So the acceleration response spectrum is quite useful in design. It really reduces the problem from a complex record of acceleration or velocity or displacement into something that is much simpler. It takes into account the maximum acceleration. It takes into account, in a way, the frequency content. However, of course, it does not take into account the duration and the number of cycles. So what you see on the left here on these figures, these are 4 records of acceleration, measured records. They all have the same peak ground acceleration, but of course, very different nature in terms of the frequency content, number of cycles, and the duration of the record. This probably becomes less important if you are looking at elastic response. When you get into nonlinear inelastic response, these kinds of effects are very important. Now, just to show you how these 4 records will look like in terms of the response spectra. These are the 4 elastic response spectra for a single degree of freedom in terms of the response to these spectra. And you can see, of course, that the spectrum captures to a large extent the frequency content depending on the period of vibration of the structure. So the benefit of having this elastic response spectrum is very clear, is that if you have a single degree of freedom system like this, you know the mass, you know the stiffness, and assuming you know the level of damping in the structure, then you can, knowing the period, you can go and work out what is the response acceleration, which basically takes into account the magnification due to the dynamic response of the structure. So the peak ground acceleration is magnified or attenuated depending on the frequency of the structure. And the benefit is that you can then reduce the dynamic problem into an equivalent static problem by taking the peak ground acceleration, let's say from a hazard map, and you then magnify this through the spectrum that you have, assuming you know the shape of the spectrum. And by multiplying this spectral acceleration by the mass, you get the equivalent static force, which is equivalent to the reaction that is applied. So the vibration at the base is equivalent to the inertial force, or the equivalent static inertial force applied on the structure. So it does simplify the problem quite a lot. And sort of the evolution of seismic codes has come effectively from this. At the very beginning, maybe 100 years ago or so, people were just designing based on experience, and then it became taking a proportion of the weight and applying it as a lateral load. With time, they started taking into account the shape of the magnification or the shape of the spectrum, and then it became more and more sophisticated, taking into account other aspects and so on. And if you look at any seismic codes now, you'll see how you can take into account the fact that the structure is multi-degree of freedom, not single degree of freedom. How do you take into account that the structure is not elastic? It can also involve nonlinearities and inelasticity and so on. But the essence of it really comes from what I'm showing on this slide here. So enough on the hazard side, and I hope it's just giving you a very brief idea on what we do in order to work out the loads on the structure. I'm going to focus more on the vulnerability side and how, knowing the loads on the structure, how do we actually try to design the structures in order to minimize the seismic risk. So, of course, what we're trying to do is avoid situations like this, where you have overall collapse of buildings, bridges, and so on. But not only that, we have to make sure that we don't get disproportionate damage to non-structural components, particularly if you have a relatively small earthquake. And of course, we learn also from what happens to structures that behave very well. So when we go to the site after an earthquake, we don't only look at structures that are damaged, we also try to understand from structures that have behaved well during an earthquake. And of course, we have to look at existing structures and how we can upgrade structures in terms of strength, ductility, and so on. And it's really important to emphasize that a lot of the existing buildings have not been designed for any seismic code. Seismic codes have started in reality in a proper form, maybe in the 1950s and 1960s, and then they started getting introduced in other countries in the 70s and 80s and 90s, and even later than that. So it is the case that there are a lot of buildings, a lot of structures that have not been designed properly and need to be upgraded all the time. And we also upgrade our codes, and we need to improve how structures are performing under these new and upgraded codes. And of course, it's not only about buildings. We need to look at bridges. We need to look at implications of earthquakes in terms of landslides, in terms of liquefaction of soil. Fires typically occur after large earthquakes because you get failure in gas pipes, and at the same time you get failure in water pipes. So you need to look at situations where fires are likely to occur after an earthquake. Even avalanches in some cases would occur because of the earthquake effects. Tsunamis, of course, very well documented. These photos here are taken from the Fukushima earthquake in 2011 in Japan. And of course, these can be devastating, and there are many parts of the world which are susceptible to the damage due to tsunamis. The only good thing is that typically you get quite significant warning, and hence you have time to evacuate before a tsunami. Now, before I start looking at codes and what kind of concepts we adopt and so on, it's probably important to say that a lot of the seismic resistance that you build in structures, you can get initially without doing any calculations by following good practice in terms of making sure that you have a proper lateral resisting system in all directions of the structure, whatever this lateral resisting system is. And then by trying as much as possible to follow relatively simple layouts as much as possible. If not, then codes will typically penalize you by asking you to do more detailed analysis and more involved design in order to make sure that you satisfy the requirements. So we can design any structure, but of course, if you use a relatively effective layout, it will make your task much easier from the very beginning. Now, of course, because we are dealing with loads which are quite uncertain, and we are also looking at probabilities of occurrence, what kind of return periods are we looking at? We need to look at that in a probabilistic sense, and we need to basically be looking at different situations as I'm showing here. So typical situation is that we look at probability of occurrence for a design earthquake of 10% in an exposure time of 50 years, which translates according to a simplified Poisson's distribution as around 500 years. So an earthquake that happens once every 500 years. In some codes, you start from an earthquake that happens 2% every 50 years or 2,500 years. It really depends. The concepts are very similar, but your starting point might be different. You can start from a small earthquake and build upwards, or you can start from a large earthquake and then build downwards and so on. So the typical probabilities or return periods that are used are either 500 years or 2,500 years. Other codes, other seismic codes around the world might use different values. So I'm going to start by what is typically referred to as performance-based seismic design. Now, this is not what exactly is in the codes. Codes are much more simplified than this. Sometimes, if it's an important structure, we might follow a performance-based seismic design, and it simply basically means that we have to have very clear understanding of what are the performance levels that we are designing for, and we also have to have an understanding of the design earthquake or the earthquake design levels that we are dealing with in terms of return period or probability of occurrence. Codes, as I said, will be inherently taking that into account, but without sometimes being transparent about what are the assumptions that are being made. So typically what we would do is that depending on the importance of the structure, so if you follow this green line, for example, here, for a typical commercial or residential structure, you will make sure that for a relatively frequent small earthquake, you will make sure that the structure has no damage, is fully operational after an earthquake. Maybe when you go for larger, rare or very rare events, you would accept that some damage might occur in the structure. It might need to be repaired, but at least you prevent collapse and you prevent loss of life. We might have to follow a much stricter objective when we are dealing with a more important structure like hospitals, government buildings, schools, and so on, and maybe make sure that you prevent damage in larger events. There might be more important structure which are safety critical, maybe which have hazardous materials and so on, where you might be a bit more strict. Now, this is transparent in a performance-based seismic design, and it's choice that is made by the designer, typically in consultation with the client. Now, codes, of course, will simplify that, as I'll show later on. Now, how do we really translate that into structural performance? Of course, under seismic loading, if you assume that this is a relatively simple structure, under seismic loading, of course, you have vibrations which are going in both directions. They are cyclic at the base, and that is equivalent to inertial loads applied at the masses within the structure. So at the end of the day, the load versus displacement response is what we call hysteretic cyclic response, and the area inside that is the energy dissipation within the system. But we would often simplify that by looking at the envelope response, or if you like, sometimes we would refer to it as the equivalent static response. And we can represent this performance-based design into a figure looking like that, where if you are pushing the structure on the ground at this direction, then it's equivalent to an inertial load applied at the masses. And hence you can look at the deformation against the reaction at the base here. And you can, as we discussed before, you can say that for a relatively small frequent earthquake, I will make sure that the structure is within the linear elastic range. Maybe if it's a larger earthquake, I will allow it to have some damage, maybe cracking of concrete and maybe yielding on some steel and so on. And maybe as the earthquake becomes larger, I would allow the structure to go into this level. But of course, that comes at the expense of damage. And of course, it means that there is a cost in terms of replacement. You are taking a higher risk in terms of casualties. And of course, it means that you might have a longer interruption of business while you are repairing the structure. If you don't like all this, then basically you'll have to make sure that it remains linear elastic, even at a very large earthquake, which is not very efficient. And it also cannot be guaranteed because we are dealing with very uncertain situations. So there is a lot of things that one can interpret from a figure like that. Now, causal practice will simplify the situation. It will target essentially one of these levels, depending on the code. Different codes might follow different approaches. The typical one is that you will follow, let's say, a life-safe approach for a 500-year return period earthquake, but then you will do checks to see what happens if you go to larger events and what happens if you have lower, smaller events. So as I said, you might follow different approaches depending on where you are in this curve. But of course, it varies a lot on whether you are in a low seismicity area or in a high seismicity area, because if you are in a very low seismicity area, you might still get away with making sure that the structure is still within the linear elastic range, even if you have the largest possible earthquake that will happen or a very rare earthquake within this area. So there are two main approaches when you're thinking about how am I going to resist these loads. You can either try to reduce the vibrations that are going in the structure, or you can design the structure for the loads or the seismic loads that you have calculated based on the hazard that you have at your site. Now, in most cases, most structures, we will follow this approach where you design for the applied loads. In some cases, you might follow the approach where you try to reduce the vibrations. And I'll show you some examples of this. So for example, base isolation is a common approach where you basically put some flexible isolators at the base of the structure. You can also do that in bridges and other structures. And the whole idea is that you are trying to isolate the superstructure from the vibration on the ground. Effectively, what you're trying to do is make sure that you are shifting the vibrations within the structure from the areas that are likely to resonate and provide significant magnification of the loads. So you are basically increasing the period of vibration of the structure by having this flexible system, and hence you are reducing the magnification that you have within the structure. And these are some examples of isolators, rubber isolators with lead plugs, friction sliders, and so on. And there are many other types of systems. You can use, of course, supplemental damping systems like this, which increase the effective damping that you have in the system. And there are many, many other types that I wouldn't have time to go through now, but you have mass damping, you have other type of active and passive vibration control systems, which gets a bit more specialized. Now, if you're designing for the applied loads, which is the more common approach, then what you will try to do, as I mentioned, is follow this approach where for relatively frequent events, you will make sure that the structure remains at very low levels of damage. If you go for rare or unlikely situation, you might accept some damage in the structure at the cost, of course, of significant replacement cost or interruption and so on. Now, the approach that is followed, if you accept that there is going to be damage at some stage, if you have large events, is what we refer to as capacity design or failure mode control, where you basically represent the structural system as a chain like this, and you make sure that if the structure is subjected to a relatively small earthquake, everything will remain linear elastic. If you have a rare event, a large earthquake, then you will make sure that parts of the structure are behaving like fuses, which are going to dissipate the energy. And then you make sure that these elements, these critical elements, are provided with sufficient ductility. All the other elements are capacity designed. That means that they are designed for the maximum possible forces that can be transferred from these ductile zones. So it is an efficient, simple, and cost-effective approach, but of course, it makes sure that you apply the capacity design approach properly and you have ductility within the areas that you can provide energy dissipation within. This approach was developed in 1970s in New Zealand and then started being applied in all other types of structure. It is now the common approach that is used in seismic codes all over the world. So for example, if you have moment resisting frames as a lateral resisting system, what you will try to do is make sure that your dissipative zones or critical zones are at the ends of the beams. Everything else is capacity design, and that's the plastic mechanism that you are designing for. You avoid having a situation where you get plastic hinges at the ends of the columns because that can lead to soft story behavior and early collapse of the structure. Of course, in research, we do quite a lot of detailed time history analysis, dynamic analysis, which is quite time consuming, but it at least allows us to come up with simplified approaches that we can use for typical structures in causal practice. So in typical structures, we normally wouldn't do nonlinear dynamic time history analysis. We will simplify the situation a lot based on calibrations that are done on a lot of analysis. But in important structures, we might still have to do verification using nonlinear dynamic analysis. And as I mentioned before, what we do in the code, because we don't know the earthquake in advance, what we will come up is an response spectrum, which is represented by this yellow line here, which is sort of idealization of the expected shape of the spectrum that you are likely to get in that particular region. So it is all simplified, but it is calibrated properly based on a lot of detailed analysis. Now, the other thing that you need to take into account is, of course, that in practice, you don't want to do nonlinear analysis. So how do you take into account the fact that you are allowing ductility and inelastic behavior in the structure? And this is what we refer to as a behavior factor or force reduction factor or force modification factor, depending on the code that you are using. So this is really a simple approach, and it is very simple, very crude, but calibrated for typical structures, where you just really, rather than designing for elastic forces, you design for smaller forces, and you make sure that you account for the ductility demand that you get because you have designed for smaller forces than the elastic forces that are induced in the structure. So again, this is embedded in causal practice, and effectively what it does is that instead of the designing for the elastic response spectrum, you can design for smaller loads, provided you take into account the ductility demand that is arising from this. So effectively, you are designing for smaller forces, and hence you get more effective design. So at the end of the day, for the rare event, for the design earthquake, if you are in a relatively high seismicity, it doesn't really matter too much if you are in low seismicity. If you are in high seismicity or moderate seismicity, you need to provide ductility in the structure. So how do you provide ductility? And again, the codes will give you a lot of information and detailing requirements to make sure that you have enough ductility, which is consistent with the level of reduction of forces that you have taken in the design. Now, I wouldn't go through great detail in this because of time, but if you are dealing with a reinforced concrete structure, for example, you need to make sure that you prevent shear failure because it's brittle, sudden, it doesn't really provide a lot of ductility. You have to make sure that beam to column joints are properly detailed because they can be quite vulnerable. You need to make sure that you are providing adequate detailing. Forget about even seismic, proper detailing in principle in terms of anchorage, joints, concrete quality, and so on. Concrete confinement is very important because it is one of the key parameters that provides ductility within a concrete element. And these are some examples of the implications on not following proper detailing for reinforced concrete and or having shear failure occurring as a critical mechanism. The same again for steel. There are certain things that you have to follow in order to make sure that you have ductility, make sure that you have proper detailing of connections. Welded connections have been shown to be quite vulnerable, and it has resulted in significant changes in seismic codes of practice in recent years. You have to make sure that you avoid early occurrence of local buckling because it is very likely to be followed by low cycle fatigue fracture under cyclic loading. Bracing members, again, can be vulnerable because of overall buckling combined with local buckling and also issues related to connections of bracing members. So all these are very important in order to provide sufficient ductility within the structure. And of course, I can go on in terms of composite structures, masonry, timber, and so on. And codes of practice, depending on what code you are looking at, will give you information on these as well. So again, these are some implications of if you don't have enough ductility in steel structures in terms of fracture due to local buckling, failure of connections, failure of braces, and so on. Now, another thing is just to highlight the fact that when we are dealing with risk, we are not necessarily only dealing with just a single structure. Sometimes we are looking at an area, a region, we're looking at a city, or we're trying to assess a risk in a country. And we do a lot of these studies in terms of loss assessment due to possible earthquakes. I'm just going to show you an example from my home city of Cairo. So again, this is one of the studies that we carried out. It involves a lot of satellite images, understanding of the hazard, looking at the building stock, looking at networks of gas networks, electricity, transportation networks. But we're not only looking at direct damage, we're also looking at indirect losses to the economy in terms of different sectors of the economy and so on. And these kind of studies are very important in terms of preparedness, mitigation, rehabilitation studies, regulations, and also insurance. And so these studies, of course, are now a very important part of the research that we do. Now, I'm going to finish by just giving you a flavor of what we have in seismic codes. I'm going to focus here on the Eurocodes, partly because I've been involved for many years in the development of the Eurocodes, and also because my understanding is that the seismic codes in Hong Kong, once they are available, they are to a large extent based on the Eurocode. So this just gives you a flavor of what is in the code. Of course, the Eurocodes, the structural Eurocodes, involve a number of codes. The one that I want to focus on here is Eurocode 8, which is the design for earthquake resistance. But of course, in order to undertake design according to Eurocode 8, you have to have an understanding of the other codes as well. Now, this is just an outline of the contents of Eurocode 8, and this is the current Eurocode 8, which is in force. And this was published in 2004, so over 20 years ago. And you can see the different parts of the code, general rules on seismic actions for buildings, bridges, assessment of existing buildings, tanks and silos and pipelines, foundations, tower masts and chimneys, and so on. So this was, as I said, developed over 20 years ago. Each country within Europe, and the code is also implemented in other countries outside Europe, would have its own national annex where it will provide maybe some adaptation, some changes of certain parameters. There isn't a current Eurocode map for Europe which is enforced, but the new code will have a map. But each country provides its own national seismic hazard map. Now, I just want to highlight this. According to Eurocode 8, if you have peak ground acceleration on rock which is less than 8% G, that is considered to be a low seismicity region. If you have a peak ground acceleration on a rock site for a 500-year event, less than 4% G, this is considered to be a non-seismic country. Now, if I relate this to, let's say, the 0.12 G that is typically indicated for Hong Kong, then it wouldn't be a low seismicity region. It would actually fall into the moderate seismicity region. And of course, the code will give the shape of the spectrum and also will give guidance on the behavior factors that you can use, and will give you some indication of what kind of earthquake you follow for the ultimate situation and for the kind of serviceability situation, and when do you use elastic design, when do you follow capacity design and inelastic behavior. And then it will give you some guidance on what is the maximum behavior factors that you can use for reinforced concrete, for steel structures, and so on, for masonry, timber, and so on. And as I mentioned before, the regularity of the structure in terms of the shape of the plan, the shape of elevation, and so on is very important, because that will determine the level of analysis that you need to use, and also the level of behavior factor that you can use. So it has, as I said, an implication. The regularity that you use in the structure has an implication on the analysis and the level of plastic deformation that you can allow in the structure. Now, of course, this code has been produced 20 years ago. Between then and now, there has been a lot of work in terms of understanding of behavior, theoretical and numerical research, laboratory testing, lessons from recent earthquakes. And of course, that then builds into much better understanding of the behavior, direct application in industry, and of course, guidance in practical design. So we are always upgrading our codes of practice. And now we are developing what we call a second generation of Eurocode 8, which is likely, it's now almost ready. It's likely to be enforced in 2028. So it has some restructuring of the code, and it has a lot of new parts in terms of assessment of existing structure, the types of structures that are involved, the type of supportive testing that you can do for the codes. There is a lot more on energy dissipation system, base isolation, non-structural component, different types of analysis, a lot more on different type of materials that you can use in structures. So significant transformation and addition within the code. And as I said, this is because of the knowledge that we have built and learned over the last 20 years or so. I'm not going to go through the key changes, but again, you can find this in a lot of guidance documents that are going to be available. And of course, at the end of the day, what I said at the beginning is that because we are dealing with a lot of uncertainties, it's really all about trying to reduce the risk. So we're trying to assess the risk, mitigate the risk, and manage the risk from earthquakes. You hear the word resilience quite a lot, mentioned as quite fashionable now, but it's really, at the end of the day, very much related to what I've been talking about. And at the end of the day, resilience is really how quickly you can recover. So if you have a damage in a structure due to earthquakes, how quickly after the event itself, you can recover the use and function of the structure. Of course, if you allow very large damage, then this will be very low resilience, and you'll have to wait for a long period until you recover the structure. So if you want a high level of resilience, you have to minimize the damage that you get in the structure. And of course, you hear a lot about disaster resilience. Once you have an event which is influencing a very large number of people, then of course it becomes a disaster. And this is on the rise, and it's on the rise because of many reasons. There is a lot of aging and deterioration in structures. A lot of structures are falling into what we call a pre-code situation. They're not really conforming to current codes. Climate change is not helping, and it's increasing the pressure on the performance of structures. There is a lot of urbanization. It's increasing it is expected that 2/3 of the world population is going to be living in cities, and all that is adding to the increased risk from earthquakes and other disasters. So I'm going just to end by this slide and really emphasize this point, is that, when I started working in earthquake engineering maybe 30 years ago, the difference in knowledge is just massive. So I would say that now any kind of disproportionate losses, like the kind of things we are seeing in this slide here, is completely avoidable, and it really should not happen. And a lot of the things that we see in the media about very large widespread damage due to earthquakes is avoidable, but for many reasons, in many cases, it does unfortunately happen. But the state of knowledge is so advanced now compared to 30, 40, 50 years ago, and there is really no excuse for having poor performance of structures in earthquake. I'm just going to end here by providing you with some references. If you need to read a bit more about this, I'll just stop here, and thank you very much for your time.
Thank you, Professor, for your insightful presentation. Now we will have the Q&A section. So if you have any questions, please raise your question in the Q&A box. All right. Here is a question. Thank you for sharing. Would you recommend adopting ductile or limited ductile behavior if I aim to reduce the pier size of a highway bridge in Hong Kong? Professor, please.
Yeah, I mean, it really depends on what level of seismicity you are dealing with. Now, if you are designing for relatively low-level earthquakes, then obviously you are going to be looking and making sure that you have enough capacity such that you don't get any damage within an earthquake. But because if you're dealing with an important bridge, an important lifeline, and it is critical in terms of the transportation network within the country, then you would need to go to relatively large events which have a very low probability of occurrence. And in this case, it would definitely be important to have some ductile detailing that would be called upon if you have this very unlikely scenario of a very large earthquake. Otherwise, you will be disproportionately designing the structure in terms of cost. So, you can make sure that the structure remains without any damage for the likely situations, but you might have to call on this for the very unlikely events. And what is the unlikely event depends on the importance of the structure. So maybe an important bridge I would design for, not for the normal 500, 2,500, maybe I would go for a 5,000 year event earthquake. And then in that situation, I would make sure that you have ductile detailing. So it really depends on the level that you are looking at.
Thank you, Professor. So let's see if we have any questions from the floor. So it seems we have no more questions from the audience. So sorry, there is a question. The question is about, since Hong Kong buildings are already designed for wind loads, can we assume that they can perform well for seismic loads, say considering pushover loading? Professor, please.
Yeah. Well, I mean, it's obviously a very relevant question. By and large, in many cases, that is the case, that in terms of capacity, at least, you are sure that a structure that is well designed for wind in Hong Kong, particularly sort of medium and high-rise structures, it is likely that the forces from wind loading are going to be larger than the forces from seismic loading. However, you cannot really generalize, and it depends on the specific situation, because it depends on the scenarios of earthquakes that you're looking at, because there are differences between wind loading and seismic loading. For example, there are higher modes of vibration that exist in buildings subjected to seismic loading that might not be the case under wind loading. So you have to make sure that the structure is performing satisfactorily under these higher modes of vibration. Also, the nature of cyclic loading that occurs under seismic situations are different from what you get under wind loading, and you need to make sure that you don't get any type of failure because of the cyclic nature of the event. But in terms, and of course, in relatively low-rise structures, again, you have to make sure that the wind is governing, because it's not necessarily the case all the time. So it really depends also on the importance of the structure, because if you have a very important structure, then you might be going to very unlikely scenarios in terms of earthquakes, and hence looking at very low probabilities of occurrence. And in that case, sometimes seismic might govern. So generally, one can assume that this is the case in terms of level of resistance, but I would caution in the case of important structures that you need to look at it a bit more closely rather than just saying, oh, the forces are going to be higher in wind rather than earthquake. I think this is an simplified situation.
Okay, thank you, Professor. So there are two more questions. The first question is about what will be the major implication on structural elements if Hong Kong publish the seismic code, such as the transfer plate and column size. And the second question is about many high-rise buildings in Hong Kong consist of transfer structures. Are they vulnerable to seismic loads? Yeah. Okay, please, Professor, please.
Well, I mean, we will have to see what kind of code eventually gets published in Hong Kong, because I have not seen it. But I would say that it really depends on what is provided in the code. However, of course, if you have transfer structures, transfer elements and so on, this is not a structure that lends itself straight away for ductile behavior and capacity design and so on. However, given that the hazard is not very high in Hong Kong, it might well be that if these structures are governed by wind, then it would be really just a matter of due diligence and checking that this kind of ductility or capacity design behavior will not be called upon in these structures. So it might well be that elastic behavior would still suffice in these cases. So I wouldn't say automatically that any structure with a transfer girder or whatever will not be satisfying the code. It really depends on the specifics of the structure. So in many cases, it's likely to be okay if it is well designed. But again, I mean, I am just really making a lot of assumptions here on what is likely to be in the code once it is published. So I wouldn't be overly worried about this, but it will mean that you have to make sure that you assess the structure for the new regulations that are existing. What I also should say is that you probably noticed when I was talking about Eurocode 8 that there is a part related to assessment of existing structures. And when we are assessing an existing structure, we tend to be a bit more relaxed about the requirements because, of course, we are dealing with an existing structure. We know already what's in the structure, and we know what are the implications of requiring any significant rehabilitation work to the structure. So when we deal with existing structure, we deal with them in a different way to the design of new structures.
Okay, thank you, Professor. We got one more question. Any further study about how the cyclic loads affects the pre-stressing concrete structures in terms of ductility and strength? Professor, please.
Yeah, I mean, again, of course, if you are dealing with a pre-stressed structure, you may have to make sure that the pre-stressed elements are not really subjected to significant ductility demands. So you would make sure that if you are required to dissipate energy in a structure, which is pre-stressed or post-tensioned and so on, you would make sure that there are other elements, for example, the connections between elements or specific elements, which can provide the ductility and dissipative behavior within the structure. But of course, it is not possible that you allow the actual pre-stressed elements to dissipate energy because they don't automatically lend themselves to this kind of behavior. But we can make sure that the joints between elements or certain fuses are inserted within the structure in order to perform that role.
Okay, thank you, Professor. And I think we have answered all the questions, and there is no more question from the audience. So thank you all for your time. So this is the end of our webinar today. And thank you, Professor, once again for your insightful presentation. Thank you all.
Thank you very much.
Thank you very much. Bye-bye.
Bye.